Okay, so just now I mentioned about the Laurent transformation and the Gallium transformation, and I also mentioned that if you substitute the Gallium transformation into the wave equation, then it becomes another form. So it doesn't keep the same law for different reference frame. It does not match the assumption for the postulate of the relativity. So let's see why it would like that. So here on the left hand top left corner we have the wave equation. Of course here without the E or B, or just it doesn't really matter. We can only consider it as an operator. So take the second derivative of the time of the space to something. Yeah, so it's just act like an operator. And then here we have the Gallium transformation. We have t prime equals t, x prime equals x minus vt. So this is the Gallium transformation I just mentioned. Okay, so now if we like to take the derivative, the partial derivative of x, and then we would like to express it in another reference frame. So we need the chain rule for multivariable. So for the other reference frame we have x prime and t prime. So because here we have xt, here we have t prime x prime. So suppose we need to take the partial derivative of x. So we have a partial derivative of x, but here we have x prime here, t prime here. And of course, partial x prime, partial x, here we can see that partial x prime, partial x is nothing but 1, nothing but 1. And then, so this is 1 times this one. We have this term, and then partial t prime, and then here, partial t prime, partial x. Partial t prime, partial x. T prime is not related to x, so partial t prime, partial x is 0. So we only have this term. So we have partial x equals partial x prime, so no problem. If we further go further for this process, we can also find that the second derivative of x, the second partial derivative of x is actually the second partial derivative of x prime. So yeah, for the x prime, there's no problem. But for the t, if we take partial t here, partial t, and then also here we have x prime, t prime. So there will be some problem because you can see here partial x prime, partial t, partial x prime, partial t. So we have a negative v here. So we have negative v multiplied by this partial x prime. And then we plus this term. So we have partial t prime and then partial t prime, partial t. So partial t prime, partial t is nothing but 1 here because yeah, you take partial derivative of t. Yeah, so it is 1. It is 1. So we have 1 times this one. So we have plus partial t prime. Okay, so here we have another term. It does not like partial t equals partial t prime. We have this term due to here because x prime is related to t. So this one is has this term. And then you can further do the second derivative of a t. Then you can feel like, oh, it is quite deep complicated, and then it becomes partial t prime, partial t prime square, and then plus v square of this term minus 2v like this. So rather than getting these two terms, of course we hope the wave equation will still look like this in other inertial resonance frame. But actually, if you only use the Gallium transformation, it will generate these two terms. Or actually, you can just move over this one to here, so it becomes 1 minus v squared over c squared multiplied by this one, and then this one is still the same term, but we have also addition of this term here. Okay, so this is the invariant of the physics law for the Gallium transformation. actually, if you are interested, you can use the Laurent transformation, substitute into here, and then you will find that okay, in the S prime reference frame, the wave equation will look like the same. Yeah. Okay, so let's go back to here. So that's why we need to study the relativity. So it tells you that when there is a star war, then what you should make, what decision you should make， 就是发生星际大战的时候，就是你应该做怎么去抉择，就是那这个题目就是非常的热血澎湃，所以我也会用中文跟你们说一次题目在说什么。So actually it says an Earth starship has been sent to check an Earth outpost on the planet P1407， 这是一个地球的星际船，就被派遣去那个P1407的那个星球啊，去查看一下那个地球的哨站啊。So whose moon houses a battle group of the often hostile reptilian 啊，就是在这个星球的卫星，就是月球上面呢，它就住了那个敌对的蜥蜴人的那个战斗群啊。So as the ship follows a straight line course, first past the planet and then past the moon， 那只船呢，就是直线的直奔那个星球 ，and then 经过那个月球，然后 it detects a high energy microwave burst at the reptilian moon base, and then 1.1 second later an explosion of the Earth outpost, which is 4 times 10 to the 8th meter from the reptilian base, as measured from the ship's reference frame 啊，这就有点长了，就是说它侦测到啊，就是从那个就是那个居住那个蜥蜴人的那个卫星基地上面呢，就是有一个高能的微波脉冲，就是侦测到嘛。然后1.1秒之后啊，就是地球的哨站就爆炸了。那这个哨站是在4乘以10的8次方米以外的 ，OK， 就是按照那个船的那个 reference frame 来计算的 ，OK，so the reptilian have obvious attack the Earth outpost， 他就说哦，蜥蜴人就是明显有攻击我们那个地球的哨站。And so the starship began to prepare for a confrontation with them。那所以那个星际船呢，就要准备去跟他们宣战。那the speed of the ship relative to the planet moon is 0.98 c， 就是船的速度是0.98倍的那个光速。What are the distance and time interval between the bursts？and explosion as measured in the planet moon frame， 那就是问那个距离跟时间呢，就用那个行星月球的那个坐标系，就是不是船的坐标系来看 ，OK。Okay, so here we denote explosion as E, short form as E, and then the burst 就是那个脉冲，就是 B， okay, so suppose the starship is stationary， 就是那个船是静止的 ，okay, so delta X equals XE minus XB。Okay. XE minus XB. So this is the explosion. This is the burst. So this one explosion. This is a burst. So this is like the weapon. 就是那个电磁脉冲炮啊，就是 就是现在的浴场，就是那个蜥蜴人的船啊，就是发射了那个电池的脉冲，然后打到那个星球上面，然后就爆炸了。现在是这样的感觉。Okay, so delta x is xe minus xb, so which is like 4.00 times 10 to the 8th power meter. So this is this one, measured from the ship reference frame. Without the prime, it is this is without the prime. So we don't have prime here. Okay. So delta t is Te minus Tb, which is 1.1 second. This is what we get. So 1.1 second later, also measure from the ship. Because if the ship is moving away from the planet moon, which is like you can regard a ship is stationary, and the planet is moving away backward. Okay. So now we need to calculate delta x prime, which is the distance measured from the planet moon reference frame. Okay, so delta x prime will be gamma delta x minus v delta t, like this. Okay, so here gamma is related to this one. This is beta. Beta is 0.980. Okay, so we have gamma equals 1 over square root of 1 minus 0.980 square. So this value is 5.025. Okay, so we have a 5.025 times delta x. Delta x is this one, 4.00 times 10 to the 8th power, and then minus v is 0.980 times c, and then, or maybe I can just write the value, 2.998 times 10 to the 8th power, and then times delta t is 1.1, like this. Okay, so this is actually 3.86 times 10 to the 8th meter. This is the distance measured on the moon planet reference frame. And then next, delta t prime. Delta t prime will be gamma times delta t minus v delta x over c squared. So this is nothing but 5.025 times delta t 1.1 minus 0.980 times c, and then times delta x is 4.00 times 10 to the 8th power all over c squared. Of course, c is 2.998 times 10 to the 8th power. So this value will be negative 1.04s. This is a negative value. Which means that this is actually Te prime minus Tb prime. If this is negative, which means that this one occurs first, this one occurs later. Because this is smaller, this is larger, this one occurs later, which means that the planet exposed before the reptile ship has the microwave burst. 就是在那个蜥蜴人发炮之前，那个星球已经爆炸了，所以蜥蜴人是无辜的啊，蜥蜴人是无辜的。Okay, so what is the meaning of the minus sign in the value of delta t prime? Okay, so here b delta t prime is actually Te prime minus Tb prime, Te prime minus Tb prime, which means that this is negative than smaller than 0, which means that Te prime is smaller than Tb prime. In other words, the explosion explosion occurs first. 它是先爆炸的，先自爆的。Okay. Okay, so it asks, did the burst cause the explosion or vice versa? Or vice versa? Because the explosion occurs first, so it does not cause it cannot be possible to be caused by the burst. So as the explosion occurs first, it cannot be caused by the burst. It cannot be caused by the burst. Also, you can see here is that if we assume that the burst is caused by the explosion is caused by the burst, and from that reference frame, delta x is 4 times 10 to the 8 meter, and then the delta t is 1.1 second, which means that the velocity of this information transmit using a speed of 3.64 times 10 to the 8 power, which is larger than the speed of light. But this is not possible. So actually the speed is impossible because it exceeds the speed of light. In the parallel frame, the speed comes out to be 3.7 times 10 to the 8. So it's still larger than the speed of light. Also impossible. Therefore, neither event could be possibly have caused to other event. That is, they are unrelated event. Thus, the starship should stand down and not confront the reptilian. 所以结论就是那个蜥人是无辜的，就不要对他宣战。Okay. Okay. So next we talk about the relativity of the velocity. Relativity of the velocity. So it says when a particle is moving with the speed u prime in the positive x prime direction in an inertial reference frame, s prime, that itself is moving with the speed v parallel to the x direction. The second inertial of a second inertial reference frame s, the speed u of the particle as measured in s will be this one. So it is not like we just algebraically add the two velocity together to become that one. Of course, it does not match what we have done in primary school. Of course, if the speed is pretty slow, then even you consider this case, then the difference will be very small. Okay, so here it says, suppose we have a reference frame S and then another reference frame S prime here. S prime has a relative velocity v compared to the S reference frame, and then here in the S prime reference frame we see that this particle is moving u prime to the right side when considering this S prime coordinate. So in this coordinate S, you will see the velocity of this particle will be in this expression u prime plus v, but we need to divide it by this factor 1 plus u prime v over c squared. So of course in the Gallium transformation, or in primary school, what we have learned is actually u equals u prime plus v. But if v is fast or u prime is fast, then the error will be large. So when we apply the formal test of letting c tends to infinity, in other words, relativistic equation is correct for all physical possible speed. But yeah, so you can also imagine that in the classical mechanics, we assume that c tends to infinity. If c tends to infinity, this one is 0. So this is this numerator divided by 1. So it will be shrink to the classical mechanics, classical physics formula. Okay, so why it will be like that? Why but like that? Okay, so of course we have the Laurent transformation. Delta x equals gamma times delta x prime plus v delta t prime. Okay, so if it's the other way around, you still multiply by gamma, but the v is a negative velocity, so we have plus v here. Okay, also for delta t, we have gamma times delta t prime plus v delta x prime over c squared, like this. So actually we can consider u to be delta x over delta t. So u is actually delta x over delta t. Okay, so gamma and gamma will cancel each other. So we have delta x prime plus v delta t prime over delta t prime plus v delta x over c squared, like this. Yeah, like this. Okay, so here we have a u equals delta x over delta t. Also, we will have u prime equals delta x prime over delta t prime. Okay, so here we can do some algebraic things. So here we multiply 1 over delta t prime, 1 over delta t prime here. Okay, so in this case, this one and this one will cancel. This one and this one will cancel. Okay, so in this sense, we have delta x prime over delta t prime, and then plus v. And then for the denominator, this one will be 1 plus v. This one should have a prime here. So v delta x prime, and then over c, and then over delta t prime, like this. So here we have this expression. So this is u prime, this is also u prime. So here we will have u equals u prime plus v over 1 plus u prime, this is u prime, u prime v over c square. Here we have a square. Here we have a square here. We have a square here. So this is why this equation looks like this. Okay. So this is a relative of velocity. Okay. Now suppose, so which is like, if we consider v is c, or maybe we can consider u prime to be c, which means that suppose this is a photon, so it moves in a speed of light in the s prime reference frame, and then here we have v. So now we have u prime to be c, so we have a c plus v. and then over 1 plus CV over C squared. Okay, suppose we have this one. Then C and C will be cancelled each other. So, and then we multiply C here. So it becomes C times C plus V over, here we also have C plus V. So this one and this one will cancel. It turns out to be C, which means that for the Laurent transformation, suppose the Laurent transformation is correct, then if there is a photon, of course it moves in the speed of light in the S prime reference frame. So in S reference frame, the speed of the photon is also C. It's also C. Okay, so this also verify that why the speed of light in different reference frame will be the same. Obviously. Okay, so here we talk about the Doppler's effect for the light. Doppler's effect for the light. So yeah, so it says when the light source and the light detector move relative to each other, the wavelength of the light as measured in the reference frame of the source is a proper wavelength because it is a proper length. So for the wave, it is a proper wavelength and lambda 0. And the detected wavelength lambda is either longer, a redshift, or shorter, blue shift, depending on whether the source detector separating the increasing and decreasing. So in classically, we have the Doppler's effect. Like maybe there is a ambulance, and then in an urgent case, then it will sound the horn, and then if it is approaching you, you will feel that the frequency becomes higher, and then if it is leaving you, then you feel like the frequency becomes lower because the speed of the sound is quite slow. The speed of the sound will be around 300 something meters a second. Okay, so if the ambulance is moving maybe like 60 or maybe 40 kilogram per meter, which is like maybe 60, you divide by 3.6 will be more than 10 meters per second. So it will change the frequency of the horn. So in that case, there will be Doppler's effect for the wave for the sound, and actually for here we also have Doppler's effect for the light. If the light is moving towards you, you will feel like the frequency become low, the frequency become higher, and it becomes more blue shift,蓝移, sorry, 蓝移. If it is moving towards you, then the frequency will become higher. If you still remember the Maxwell's rainbow, for shorter wavelength, you have higher frequency, so as the higher energy, which is the blue shift. And if it is moving away from you, then the wavelength become longer, the frequency become lower. So in this case, it's a redshift, depending on whether the source detector separation is increasing or decreasing. Actually, around 100 years ago, then the physician find that the Herbert find that most of the stars are moving away from us, which follows the redshift. 就是100年前就是发现那个哈勃发现那个红移的现象，所以就是它这个就是佐证了这个宇宙在膨胀的这个事实。而且最近我们就是好像是20年前的是我们发现是这个宇宙还是在加速的膨胀。Okay. So depending on where the source of so when the separation is increasing, the wavelengths are related by this equation. So this is the proper wavelength, and lambda becomes larger because it's moving away from you, so you feel like the wavelength become larger. Okay, so it's 1 plus beta, 1 minus beta. Take the square root, and then we have multiplied by the wavelength, the proper wavelength, who becomes the Doppler's wavelength. So here we have the beta to be here, and then the relative radial speed. And then if the separation is decreasing, and then we just change the sign, it becomes 1 minus beta over 1 plus beta. Take the square root of the whole term. Yeah. So for speed much less than c, the magnitude of the Doppler's wavelength is lambda minus lambda 0. Is approximately related to v by this equation. If v is much smaller than c, it is a linear relationship. I'm not sure whether you have learned the Taylor series. The Taylor series in calculus class. The Taylor series or the Maclaurin series. So you can actually take the Maclaurin series of this square root and also this one. Then you'll find that it will be, if you take the Maclaurin series of this one, you'll find that it will be like 1 minus beta will be something like 1, and then minus or plus beta, and then plus blah blah blah, something multiplied by the beta square, something multiplied by beta cube, and then so on and so forth. And then now suppose v is much smaller than c, which means that b is small. So beta will be small. If beta is small, then beta square will be even smaller. And then just like if you have a 0.1, and then you take the square will be 0.01, and then take the cube will be 0.001, something like that. So if beta is small enough, then we can just ignore the later term, which will be like, oh, this is beta. So it will be like this one, like this one. Okay, so yeah. So this is another case which called the transverse Doppler effect, which means that suppose the wave is propagated in this direction from D to P. Yet in the figure, a source S moves past a detector D. This is the detector. Actually, this is moving perpendicular to it. So when S reaches the point P, the velocity of S is perpendicular to the line joining PD. And that instant, S is moving neither toward or away from D. If the source is emitting sound, blah 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 blah, then yeah, there will be some difference. This one, yeah, it is moving either towards or in the other way around to the source. This one is moving actually perpendicular to the source. Yeah, so there's still a Doppler effect, but of course the the equation is a bit different. Rather than having this 1 plus beta over 1 minus beta square root, it has something like 1 minus beta square, take the square root. Okay, so for low speed beta much less than 1, this equation can be explained in a power series, which means the Taylor series or the Maclaurin series in beta, and approximates this one. That's this one. Okay, so we have which is like a square root of 1 minus x. If x is much less than 1, then it will becomes 1 minus half, approximate as 1 minus x. So here x is a beta square, and of course later on there will be something plus something x squared minus something x cubed, something like that. Maybe, I'm not sure plus or minus, but yeah, this is, yeah. So you can check it out if you're interested. You can use the method for the Taylor series to check the coefficient of the later term. So the first term will be like a 1/2. Usually, if you assume that beta is much less than 1, then usually we just pick the first two terms like this. So again, the relativistic effect for low speed light and the detector appear with the beta square term. So if beta is much larger, then we need to consider the beta square term, so on and so forth. Okay, so now we consider the momentum and energy. Yeah, actually, relativistic is very interesting. Just now we mentioned something, the low supernova explosion, 超新星爆发, also the Star War, and actually we also consider something like the small particle. So here in relativistic mechanics, the definition of the linear momentum is like this: P equals gamma mv. Of course, in classical mechanics, we have P equals mv. We don't have this gamma factor, because if v is small, gamma is nothing but 1. So yeah, it looks okay. So the next one is that this equation gives the correct definition for the momentum for all physical possible speeds. For speed much less than c, it reduced to the classical definition. So because if the speed is much less than c, which means that beta is small and then gamma will be close to 1. Yeah. So yeah, like this. So an object mass m and the relevant and the equivalent energy E0 are related by E naught equals mc squared. E naught, which means that if the mass is stationary for this reference frame, then this is so-called the rest energy. The rest energy. So the rest energy of this object is mc squared. Which means that if an object has mass, if all the mass transform to energy, which means that if the object is vanished, and then it will become energy, and the energy is as large as m times c squared. This way it will be very large. If you consider maybe my weight is around 70 kilograms, multiplied by c squared, 2.998 times 10 to the 8th power. It will be a very, very large value. Something like 10 to the 17 power joule. But of course, I will not vent this. So all the energy you keep here. So which, without the subscript 0, is the best known science equation of all time. So 以小学生都知道啊，什么 E 等于 mc squared， 现在他们不知道什么意义嘛。So this energy E0 that is associated with the mass of an energy object is called the mass energy or the rest energy. 静止的那个能量。So the second name suggests that E0 is an energy that the object has even when it's at rest, simply because it has mass. 就是有质量就有能量，所以这个是质能方程式嘛，就是质量如果变成能量它质量就相当于那么多能量。So if we assume that the object's potential energy is zero, then its total energy E is the sum of the mass energy and its kinetic energy. So the total energy of a moving object will be like, this is the rest energy, mc squared plus k. K is the kinetic energy. Of course, this is not half of mv squared. In classical mechanics, k is half of mv squared. Or in the next chapter, you will know it as p squared over 2m. Because mv is p, so you can multiply m here, so that becomes mv squared, which is p squared, and then of course you should divide m also, so we have 2m at the bottom. So in classical mechanics, k is p squared over 2m. Here, k, we have mc squared plus k, and the total energy will be gamma times mc squared, which means that k is gamma minus 1 times mc squared. Okay, so you may ask, so we have the mass energy, and we have mass, but this mass cannot change to energy. So how is this useful? But actually, it is related to the nuclear reaction. 就是我用中文来说吧，就是你们知道核反应吗？就是那个如果现在我们核能发电的话，其实核能它主要分成两种嘛，一个是核分裂，一个是核融合啊。那核分裂的话，就是那个是物理嘛，就是其实就是所有那个元素，你学那个元素周期表，那你学的那个质量数通常你都当作是一个整数就是高中化学的话，你都当作是一个整数。那实际上你查那个元素周期表的时候，它就不是整数的，它后面小数点有几位。那实际上，你会看到就是最轻的那个元素，单个原子，就是单个原子来说，不是单个原子，单个质子中子来算的话，最轻的是铁，所以如果比铁，原子序高的那个元素，它会走那个核分裂的反应，那它就是会透过那个失去它的质量来发出能量，所以就是比如说我们熟知的铀元素，就是一个很重的什么铀238，就是那个质量数，那它就是透过失去能量去产生能量，就是包括现在核子发电。或者是那个原子弹，它也是用那个核分裂是它背后的原理。那核融合的话，目前来说还没有掌握很好。那我们所知的氢弹就是一个核融合的反应，但是核融合去发电的话，我们还不行，就是因为它需要很难的控制，就是核融合它发生的话，它需要温度很高。就现在的话，比如说一个氢弹，一个氢弹要爆炸的话，它是先需要一个原子弹爆炸所产生的能量，才能够点燃一个氢弹。所以为了引爆一个氢弹的话，你要先有一个原子弹，你才能够产生那个温度，让那个氢弹去爆炸。 那核融合的意思，它就是比铁轻，比铁那个原子序比较低的元素嘛，那最低就是氢嘛，那氢就是原子序1嘛，那只有一个质子嘛，中子都没有，那它变成变成氦啊，变成氦的时候，它也会失去质量，发出能量，那最轻的就是铁。所以，如果那些星球啊，它最稳定的状态就是铁，最稳定就是铁。它可能透过核反应、核分裂的从重的元素，它就会跑到铁。轻的元素氢，它一直在爆炸的话，它也会一直变变轻，然后原子序一直变大到铁，它就停下来。OK， 所以就是说我们肉眼能看到，我不确定肉眼能不能看到，就是那个猎户座的那个圣修士，就是在那个猎户座，那它就是一个就是红巨星，就是去年的时候，就是有人发现它就是突然变暗，它是不是快要超新星爆发了？他后来发现就不是，他那个红巨星，它就是一直在行那个核反应，它就是元素一直跳到最后，它全部核融合的反应都没有办法进行的时候，它就开始塌缩，因为它一直在核反应的时候，它就温度很高，它就膨胀，然后去抵抗那种塌缩的那个引力，所以它就会维持着一个大的体积，所以等它点燃结束的时候，它就会一直塌缩，然后它就所有物质就会压在一块，然后最后也压到最后，它就忍受不了，它就爆开来。那其实太阳也是一直在走那个核反应的嘛。Okay, so here we have a kinetic energy, which is actually the total energy minus the rest energy. So which is gamma mc squared minus mc squared, which is gamma minus 1 mc squared, like this. Okay, so where gamma is 1 over square root of 1 minus beta squared. So which is nothing special. And here this figure shows that yeah, of course, in the classical mechanics, we know that K equals half of mv squared. And if we use this gamma minus 1 multiplied by mc squared, then this curve will look like this. It tells you that first point is if the v over z is small, if the beta is small, they match each other. Also, you can use the Taylor series to expand this gamma. You use the Taylor series to expand it. Then you will find if beta is small, then the first term will be 1 over half of mv squared. So this is the first point. And the second point is that if we just follow the classical mechanics, which means that this case, this is speed of light. This is beta equals to 1, which is the speed of light. It tells you that if you give sufficient energy, if the kinetic energy is high enough, this velocity should be able to higher than the speed of light. But it doesn't happen. I just mentioned yesterday. But if you follow this one, you know that if v over z is large, then this term will become very, very large. It will diverge. Actually, this we can never approach z because here the energy becomes very, very large, but it cannot approach this speed of light. So it will diverge. It will diverge, increase very, very quickly. But it can never reach the speed of light. So the second point of this figure. So okay, maybe I stop here, and then I'll see you next week because I need to show the derivation of this equation.